once again the final PhD defense of Prabhat Bana. He has been supervised by the former Associate Professor Muhammad Amin at the Department of Electric Energy and co-supervised by Professor Roy East. Together with us today we have first opponent, which is full Professor Ling Fan. She's from the University of South Florida. She's an editor-in-chief of IEEE Electrification magazine and an associate editor of IEEE Transactional Energy Conversion. She has become an IEEE fellow for her contributions to stability and control of inverter-based resources, which is quite relevant to the thesis of the candidate today. In addition, we have a second opponent, which is Sergio Vasquez Perez, who is an associate professor at the University of Sevilla. He has around 200 publications in the area of power electronics, multi-level inverters, and predictive control. How we are going to do this as follows is that Prabhat will get opportunities to present his thesis for the first 45 minutes from now on. After that, we will have a 15 minutes break. Then we will have a session with Professor Ling Fan. She will ask you questions and challenge you. And we will have some back and forth answers and question answers and follow-up questions. When Ling is done with her discussion with you, we'll move over to the second opponent with leftover questions from Sergio Vasquez Perez. I am the coordinator of this, so I will not ask any academic questions, but I will coordinate it from the department side. I'm Jonas Christiansdøren, associate professor at the Department of Electric Energy. So let us first give the floor to you to present your thesis for the next 45 minutes, and we all look forward to that.
Thank you, Jonas, for the introduction. Okay, thank you everyone for joining the defense session as well. I'm very delighted to present you on my PhD research, Advanced Control Design for Grid-Connected Converters in Renewable Energy Applications. So this is basically an interaction of the power converters and artificial intelligence, which are the two technologies that are rapidly evolving and will play a crucial role in integrating the renewable energy sources to the grid. So this is the outline that we will cover today. I will take you through the background first, scope and objective of the research that we set out to achieve, and methodologies we proposed to achieve a sustainable energy structure. So afterward, I will conclude the presentation with a summary and future work. So let's start with the introduction first. So if we'll see the conventional power system, which were dominated by synchronous generator systems, the traditional controller used to work fine. However, considering the rapid integration of renewable energy sources such as PV and wind, the control philosophy needs to be changed. That is because the standard controllers, the linear controllers, might not work satisfactorily because of some challenges such as
we don't see your screen.
But I am already sharing this. Can someone confirm if you are seeing my screen? Okay.
Yeah.
So the standard control philosophy needs to be changed considering the rapid integration of renewable energy sources such as PV and grid. That is because of the inherent shortcomings such as the inability to extract the maximum power from the renewable energy sources and smoothly transfer it to the grid. And bandwidth limitation, because we are using several linear control loops to achieve multiple objectives, so we define separate bandwidth. And since they are dependent on the system model or parameters, so they may not work satisfactorily during parameter uncertainty conditions. And of course, there is stable interaction among the system and controller. But we will discuss these challenges individually. So, and those can be more clear if we'll consider a relatively simpler system, which here is grid connected VAC. And at the input, we can connect any renewable energy source, PV, wind, or battery energy system. So the typical way of controlling such a system is to have a inner loop current controller by considering the feedback signal reference current and actual DC and AC side signals. It will be manipulating a reference voltage signal that we discussed during the trial lecture. So after processing it through a PWM stage, we will be generating the switching signal to control the converter. So some of the challenges that are associated with the linear controllers are better reference tracking and harmonic profile, and there are oscillations that are introduced during dynamic conditions, and could be fault limiting if you are running in grid farming mode, and of course there is bandwidth limitations. So in the state of art, what they are doing in the literature is they are introducing active damping on the AC side to damp out the voltage oscillations, or you can make the linear controller to be more adaptive if you will tune its gain online. And otherwise, you enter into a different control philosophy, which is non-linear controller, mainly kind of, for example, model predictive controller. So that is also one of the objectives of my PhD work. And also recently, researchers have started exploring the artificial intelligence. So that is also the main focus of this work. So we'll see how we are achieving the solution to these challenges. But considering at the input side, you are going to have renewable energy sources. So this reference current is no more a constant signal. So this has to come from an outer loop. So depending on the type of objectives we're setting out, it could be a combination of several outer loops that will be generating your reference signal, reference current signal. So some of the challenges that are associated with the outer loop are maintaining the DC voltage balance, and again oscillations during transient condition, and you need to implement the maximum power point algorithm in order to extract the maximum power from these renewable energy sources. And since they don't contribute any inherent inertial response or voltage support to the grid, so those two features can also be taken into account. And if you are addressing those two challenges through battery energy sources or supercapacitor, then you need to also consider the state of charge control. So in the literature, how they are handling is they are again introducing active damping to damp out the DC side voltage oscillations, and some optimization based MPPT algorithm to address the maximum power point tracking issue. Although they manage to track well, but that will add more control complexity and computational burden to the system. But we will see how we have addressed this challenge. And if you are targeting the frequency or inertial support and reactive power support, then they are opting for synchro converters or virtual synchronous machine emulation schemes. So with those challenges and solutions, the scope and objectives that we set out to achieve are first, to review and implement the advanced current controllers. So that will answer the question if the standard current controllers are fast enough or they're able enough to handle the dynamics that is coming from the renewable energy sources. And when you are integrating the renewable energy sources to the grid, can the standard control extract maximum power from it? So that we will focus on in one of our work. And then can we provide some ancillary services like inertial response or frequency support with the grid connected renewable energy systems? So while answering those 3 points, those 3 research questions, we have contributed these 4 points, and the outcome is actually published in 5 journals and 5 conferences. But we will discuss the individual contribution in the same sequence. So let's start with the first contribution, which is ANN based inner loop current controller. The objective of going for ANN based inner current controller will be clear towards the surprisingly towards the end, not at the beginning. So, but anyway, we have published the work in one of the IEEE journal and conference. So how we are doing here is we are collecting some control inputs as data and control output data. We are storing it in a lookup table, and we are using it to train the NN controller. So depending on the type of controller or coordination, I mean, whether it is DQ or alpha beta frame, so you will collect the input data, which here are output inductor current, this one, and its reference value and the PCC voltage. So all those 6 signals will be stored the input matrix called X, and we are targeting the modulation signal, or you can say voltage reference signal, whether it can be DQ or ABC reference. And we have relatively considered a smaller system, which is kind of 1 kilowatt, and we are going to use this to validate in the simulation and experimental environment. So how the training is done is, the first process of ANN training is to collect the data. That is the more like challenging stuff to do to train the ANN. So what we did is, we have collected a 300,000 sample of data and stored it in the input matrix X, and the output, which is voltage reference, stored in M. So those data are obtained under 3 conditions, which are reference current change, grid voltage change, and input voltage change. So once we are storing it offline in the lookup table X, so that input X will be multiplied with weight factor, certain combination of weight factors, and will be added with the bias values to obtain this internal variable U1. So now the next step is to process it through an activation function. Here we have considered the tangent hyperbole function, but it could be other activation functions such as ReLU and others as well. But that doesn't make a significant difference in our work, so we stick to tangent hyperbole. So you process it through this activation function, and you repeat all these 2 procedures at the output layer again to obtain the final predicted output out of the neural network. Then the next step is to define a cost function to effectively train your neural network. So how that is done is, we are basically taking the mean square error of predicted value and the actual output that we stored in the lookup table. So now the goal is to minimize this cost function with respect to weight values and bias values in order to get their updated value. So that is our next step, which is called as the back propagation. So you calculate this gradient and update the weight and bias values at this step, and the loop continues until and unless you get a you minimize this gradient of the cost function to a lower value. So for the representation, I have presented here the PI controller, but we have also done the same procedure for the MPC controller as well. Because as I said, the ANN controller can actually retain the performance of nonlinear controllers, but with a lesser computational burden. So that's what we saw the conclusion in the trial lecture, but we'll see how it is going to do. So once the training procedure is done, as you can see here, the ANN controller that was trained under the PI controller data that was minimized to a very lower value, and same for the ANN controller trained under the MPC data. We are naming it as ANN MPC and ANN PI. And here also you can see that the regression value is almost closer to unity in both the case. That indicates a better fitting or better training of the neural network structures, and they can be deployed online for the performance testing. So we have obtained the results under two scenarios, which are reference current change and the grid voltage sag condition here. So one noticeable difference you would find here is the current waveform that is obtained with the PI controller family, with both PI and NNPI, that is a bit more noisy compared to the MPC. And that is why you also see an improved TSD in case of the MPC family. But although the MPC scheme, although it achieves better performance, improved TSD, lesser noisy, but it will bring up the additional computational burden to the table. So to tackle that challenge, we can actually go with the ANN controller that will be trained under the MPC. So that could be an alternative solution. And also while doing that, you can see here we did a mathematical calculations like how many number of calculation the MPC does in a particular sampling instance. So what we found is it's a very huge number, 135 into the power 6 in case of MPC. Whereas in case of the ANN, it's only 126. So there is a drastic reduction in the number of calculations. So that gives an indication that when you go for the real-time implementation, the ANN controller will actually utilize less resource of your controller. So that was the outcome of this analysis. But then we also thought, instead of exactly mimicking the supervisor controller through ANN, can we actually improve the performance compared to the supervisor controller? So for that, we came up with a physics-informed ANN controller. We are naming it as physics-informed because the input data we are processing to the ANN controller are the two current errors in the DQ frame, which is ED and EQ. Because ultimately, if you'll see, the PI controller objective is to minimize the current error that you are feeding in DQ frame or alpha beta. So since now the objective is known to the neural network controller that it will minimize the ED and EQ and produce the voltage vectors, reference voltage at the output. That is why we are naming it as physics informed. So the difference here you can actually see with the earlier ANN controller, we are feeding all the 6 inputs, which are reference current, actual current, and VCC voltage. However, in the physics informed controller, we are only using 2 control inputs, which are current errors and DQ frame. So let's check the performance. We actually train the physics informed ANN controller in the similar way that we did earlier. So the results that are shown here are obtained under the reference current change. So if you'll see here, I forgot to mention one thing. The system we have considered here is the converter is connected to the DC source through a DC cable here. So we have considered this system just to mimic or give a vibe of offshore wind farm, because this is a common choice of integrating the offshore winds and HVDC applications. So that because of that DC cable, whenever there is a change in reference current, you will experience certain oscillations in the PCC voltage. However, if we'll see in the physics informed ANN case, those oscillations are relatively damped out faster. So that indicates the advantageous feature of the physics informed ANN controller. But actually, although we have achieved better performance through the physics informed ANN controller, but the reason was still unclear to us. What made it to achieve this? So we tried to explore the black box nature of the ANN controller through small signal modeling and tried to do the stability analysis, how it interacts with the system as well. So for that, what we did here is we collected all the differential equations by applying the KVL on AC side, DC side, and the controller equations, and considered it as a typical power system problem. And then where X indicates the states of the system, U is the control input, and we did the linearization and then applied the Taylor series expansion and ignored the second and higher order terms to end up at equation 10. So from where the A indicates the system matrix, and we can consider this a matrix to analyze the eigenvalues and determine if the interaction is stable or not. But before that, we need to verify if the derived small signal model for this ANN controller is accurate or not. So for that reason, we have compared the results that are coming from the stress test model, derived stress test model, and the nonlinear simulating model. So we did a reference sense current at 0.4 second. And as you can see here, the stress test derived small signal model is able enough to capture all the oscillations that we got from the simulating model, which indicates the preciseness of the derived small signal model, and also indicates us to we can actually consider this for the stability analysis. So that's what we did here. We collected the eigenvalues obtained with the PI controller and with the ANN controller. As you can see here, the eigenvalues that are associated with the PCC voltage and output current, they have almost double the damping factor in case of the ANN controller. It was -7 almost, and it was -14 almost in case of the NN controller. So that was the reason why we achieved a relatively better damping in the time domain waveform that I talked in 2 slides back. So apart from that, the other different noticeable different thing we see here is the states that are associated with the PI values. Because in case of the linear PI controller, we have two integrators in the D and Q axis reference frame, right? So that will contribute 2 states. So because of that, we see 2 eigenvalues here. However, in case of the ANN controller, since we eliminate the use of PI, it's just combination of certain weight and constant weight and bias values. We don't see any states here. That is why it is non-existent here. And the remaining eigenvalues that are associated with PLL, DC side dynamics, they are almost the same in both the cases. So that makes sense. There is not insignificant stuff we are doing in ANN controller. And also conducting the simulation in the nonlinear model is always time taking. So that's why we try to analyze the eigenvalue trajectory. So what we did here is we varied the grid side inductor value from 0.2 to 1 per unit. So that indicates the extremely weak grid condition. And under that cases, the eigenvalues that are associated with the PCC voltage and inductor current, they are actually moving towards the unstable region. However, they are still in the negative half of the complex plane, which indicates the interaction between the ANN and system is stable. So that proves the stability and also gives us an indication how the physics informed ANN controller was able to damp out the oscillation faster. But we also, on top of that, we did impedance frequency analysis. This is also kind of tool to analyze the stable interaction. However, we only did it just to check how their impedance behave in the frequency domain. So that is why we have considered the standard sequence domain impedance analysis, where we are injecting the sound current in positive and negative sequence, and we are deriving the impedances in positive and negative sequence, which are ZP and Zn. So if we'll see the impedance plots, you can actually see here the ANN controllers that are trained with the MPC, they are able to capture the same dynamics of the MPC. However, in case of the PA domain, you see a little divergency in the below fundamental frequency. It is at least the angle plot is kind of giving a resistive behavior in case of the ANN controller, and that is the reason why we maybe saw a better damping. So from this analysis, what we can conclude is if you'll train the ANN in a correct way and in a better way, then it can actually mimic the performance of its supervisor controller, and in fact can provide better solution. And the interaction is also stable. So that is why we went on to integrate the NN controllers for the renewable energy sources and check if it is giving the satisfied responses. And the outcome are published in these publications. So before moving depth to the controllers, first I would like to introduce what kind of PV system we have in the literature. So the first one is a double stage grid connected PV system, where we are connecting the PV to the grid through two stages. One is DC-DC and one is DC-AC. So the DC-DC converter will take care about the MPPT control unit, and for the voltage source converter, we will implement the current controller that will be taking care about the output inductor current. However, in case of the, so that is why the control structure is a bit relatively simple, because you are dividing the control structure into two parts. However, in case of the single stage system, we eliminate the use of DC-DC converter, right? So in that sense, we can actually say it will save a relatively cost for you. However, that will bring the additional control complexity to the system, because you only have one option to control both MPPT controller and inner loop current controller. So basically, you are going to merge them to control your system. But we will see how we have devised a control solution for the single stage grid connected PV system. In short, we can say SSGT PV. So I will divide the control solution into two parts. The first part, I will explain the MPPT controller, and then I will link it to how it is connected to the inner loop and current controller. So the figure or the flow chart shown here, it is for the standard Potter wind observer algorithm. So what it does, it senses the PV voltage and current, evaluates the power, and it again does a perturbation in the voltage to check the power at this instance. So if that will be clear actually if we look into this figure. So let's suppose you are at here at this initial operating point. So now it will do a perturbation in the voltage level up to here. So you will reach at this point. Now it will check the power at this point and compare to the previous one. So you will end up seeing you have more power compared to your previous power. That is why it will continue to perturb in the same direction, and it will end up at the reaching at the maximum power point here. And same is the case if you are on the right side of the PV curve. You will finally end up at the maximum power point. So if the logic is so simple, and if it is, as you saw, it is able enough to achieve the maximum power point or make the PV system to operate at MPP, so why people are focusing on more optimization based solution? That is because of this reason. So these kind of reasons, they are making the controller guys life more difficult. So this partial setting can be actually better understood if we'll consider a PV system configuration like this. If all the PV panels are uniformly shaded, then we'll get a single peak in the entire PV core. However, let's suppose say two of the PV panels or one of the PV panel got partially shaded. So your ideal PV curve will be no more containing a single peak, rather than we'll end up getting something like this. So now it is very confusing for the standard P&O controller that what is the maximum power point for it, which one to track it. So in that essence, it will end up maybe tracking to this point by seeing this is the maximum power point. So in that way, we will end up losing this much of maximum power, because this is our global maximum power point. So that is the reason why we suggested an improved MPPT algorithm. And since we wanted to suggest a simple control solution, we didn't go for optimization algorithm. Rather, we suggested a simple process, which is based on two steps. In the first step, what we are saying, we ask the P&O algorithm to take some rest. And in the meanwhile, we'll do a full scan operation of the entire PV core. So what actually it means is we divide the PV curve into different segments and check the power in each segment. The segment that is having the global maximum power, that will be selected as the final segment, and that information will be passed to the standard P&O algorithm. So now it will be no more confusing for it. So it will end up in tracking this. global maximum power point. So this is what we have done here. Now let's see how it works in the simulation and experimental environment. So before that, I actually wanted to show the overall control structure here, how the improved MPPT algorithm is linked to the inner loop NN controller. So the improved MPPT generates this voltage reference signal that is converted into the reference current and given as an input to the NN controller. And on top of that, it receives three more signals, which are actual inductor current, DC voltage, and the PV voltage or DC link voltage, you can say, since it's a single stage configuration. And ultimately, it will generate you the modulation signals. So we try to analyze the performance by considering this PV setting, where two of the units are partially shaded, and it is not anymore uniformly shaded. So that will result the PV curve something like this, where with the global maximum power point, it's saying your PV voltage is supposed to be 450 volt, and at that voltage point, you are going to achieve 54 kilowatt of power. This is exactly what you achieve in case of the introduced controller, because your PV voltage is getting settled at the 450 volt, and with that you are able enough to get 54 kilowatt of power from the PV. However, in case of the standard controller, if you'll see, the PV voltage is going to be settled around 700 volt here, and the corresponding power you get is around 46 kilowatt. That means it is getting settled at the local maximum power point 2 instead of tracking to this global maximum power. So that was the thing with the improved MPPT controller and ANN controller. But we wanted to check the performance of the ANN controller if we can. What will happen basically if we'll include the ancillary services at the outer loop. So for that reason, we have only considered the frequency support feature, although in a similar manner, we can actually establish the voltage support feature. And the outcome is submitted into one of the IEEE journal. So what we are doing here is, let's suppose one frequency incident happened here. So that means your frequency will drop down like this. And the IEEE 2800, recent IEEE 2800 standard says, if your PV or wind is operating at a curtailed mode, or if you are reserving some sort of power, although that reserved power has to be agreed upon the system aggregator. However, if you are reserving some amount of power, then you need to support whenever there is a under frequency event. So, and how you can do that? You can actually establish that in 5 ways of, and we say it's fast frequency response. And under the fast frequency response, the inertial response comes as a subcategory. So that can be achieved in 5 ways. One is non-controlled response, which is inherent synchronous generator. And the second one is proportional response, which is based on the frequency difference. And the step response. So whenever a disturbance happens, you respond it in a step way, but with a fixed voltage, and it may not be proportional. And the derivative response, which is kind of Rokov. And so let's see how we devised the solution and we achieved the inertial support from the grid connected PV. So we are doing it in 2 ways. One is to save some sort of power from the PV. So you can say it reserved power. So how can you do that? So instead of operating at the maximum power point, you operate at the flexible power point. So, and you keep this much amount of power reserved. And whenever there is necessary, you take out that power to support the frequency. And the second way is to utilize the DC link energy from this capacitor. Although it will be a small energy compared to this reserve power, but anything is welcome. So we have utilized these both of the energy to support the frequency. And again, as I said, this power reserve has to be agreed upon the system aggregator, because the renewable energy sources, they are already having some efficiency issues. So you need to agree upon how much amount of power you are going to reserve for this purpose. So based on those two logics, we came up with a solution, and we are naming it as ANNFFR controller. So the output is generating a power signal, which is delta PPV. So this will adjust the set point of the power that you reserved from the PV. And the second one is delta VDC. So it will adjust the DC link voltage so that you can take out some small sort of energy from the capacitor. So, but this is how it works. But the challenging stuff is to train the NN controller. So what are the input parameters that we are going to give NN controller? That is going to be an issue. So what we thought here is we defined two threshold limits for the under frequency, which is UFTH1. So according to IEEE 2800 standard, it should be 0.1%. And we defined another threshold value, which is 1% of the nominal frequency. So we are comparing the nominal frequency with those two threshold values. And accordingly, we generate two flags, UF1 and UF2. So through sample and hold circuit, we'll lock the time instance when the UF1 and UF2 triggered. That means indirectly, I am saying whenever the frequency crosses this UFTH1, we are noting this time through the sample and hold circuit. And similarly, we are also noting the T2 for under frequency. And then if we take the difference, this will give us a DT, the time difference. So this DT will vary depending on the type of disturbance. If you have a large disturbance, your frequency may fall very rapidly. And in that case, this DT will be very lower value. And since there is a cross-coupling effect on the PCC voltage, we are also interested to check how the PCC voltage behaved during that DT period. And we are noting it down as dV. So this is kind of the deviation from the nominal or steady state voltage. And we are giving these two parameters as an input to the neural network. In fact, it will be 4 when we consider the over frequency case as well. So by considering those 4 input parameters, it will give you two signals, which are delta P and delta V. So they will adjust the set points, as I said. So that's how the controller system is configured. But what are the test cases we have undertaken to collect the data for these signals? So what we have done is we changed the load connection from 100 kilowatt to 2 megawatt with a step size of 100 kilowatt. And for all the incidents, we are saving what are the DT and DV values. We got it for under and over frequency incidents. So they will be stored as input matrix. And what will be our output, the ANN going to be predicted? So those are delta P and delta V, and they are obtained by considering the maximum value of the standard virtual synchronous generator scheme. So we have implemented the VSC, and corresponding to all the events, we are saving the peak power that it is releasing to address this under frequency. So that will actually give a vibe was that whenever there is under frequency, you directly release that peak power here instead of responding it in a frequency deviation case or Rokov case. So it will be very instantaneous, and that may improve the nadir of the frequency depth. That we'll see in the results. So to validate, we have considered an IEEE 13-watt system here, where we have connected two PV system configuration with 250 kilowatt at bus number 675 and bus number 646. And what we done here is we have connected a 500 kilowatt load at the bus number 611, and that will result the under frequency event here. And as you can see, the standard virtual synchronous generator scheme, it improves the frequency nadir by supplying some sort of inertial power. However, in case of the introduced ANN FFR controller, since the release of power is very step and proportional, instantaneous, that is actually helping the nadir very relatively higher. And as you can see here, the power and voltage command, they are released in a step and a proportional way. So we have also checked the adaptiveness of the NNFFR controller by considering over frequency event. So what we have done is we have disconnected a 500 kilowatt load, and we saw the frequency, the over frequency event. And instead, so now the NNFFR controller releases a step power and step voltage signal. So that will help in reducing the power which it was supplying earlier. So, and in the recent standards, although you are that is optional if to support the under frequency event. However, in the distributed PV systems, they are actually having this over frequency support. So because that is easy, you don't have to save some sort of headroom power. So they are already coming up with this solution. But for the under frequency event, you need to save some sort of reserve power. So this actually proves the adaptiveness of the NNFFR controller, because it is very it releases basically the signals according to the type of disturbances. So based on those outcomes, I will try to summarize the presentations. What we have done here is we tried to explore the trade-off between the linear controller and nonlinear controller by entering into the artificial intelligence domain. So what we saw here is the nonlinear controller can actually achieve better performance. Nonlinear controller means, I mean here the MPC. However, it will bring you the more computational burden to the system. So that computational burden can be actually reduced if we'll use the ANN-based controller. But actually, if we'll train the ANN through strongly physics informed data set, then we can actually achieve better performance than their supervisory controller also. And to reveal how we are getting better performance, we have conducted the small signal analysis. So that gave us a vibe how it interacts and if the interaction is stable or not. So once we got from that, we employed the NN controller for PV integration, which is an example of renewable energy sources. And we saw that the interaction with the improved MPPT algorithm we suggested is pretty much stable, and it is able enough to extract maximum power from the PV and transfers smoothly to the grid. So, and we also tried to explore with that set of controller scheme, can we establish the ancillary services such as frequency support scheme? So for that reason, we have proposed one ANNFFR controller for that. So it is very adaptive and responds in accordance with the type of disturbance. So that's the conclusion I wanted to make. But as a future work, I would like to say, if I would have time for to do the PhD research more time frame, then I would have continued in this way. Mostly our work focused using the ANN as a controller. But actually there is a very potential area where we can actually use the ANN as a stability analysis tool. Because most of the wind farm and the PV system, they come as a black box system. So you can actually use the ANN as a stability tool to either analyze the impedance frequency domain. And the other aspect is you can, for the grid connected PV system, you can train your NN controller with a strong physics dataset. And the ideal choice for the inert cell support is a hybrid PV battery system, right? But we have shown the application only for grid connected PV. So the same control, the same NNFFR controller can be actually used to control the battery or supercapacitor, say, to have a very faster and instantaneous frequency response scheme. And we have mainly focused on the inert cell power response. However, similarly, the reactive power support can be also be established. So that's what I wanted to say. Thank you for your attention.
Thank you so much. We will minutes break before we have go through with the opponents. So, okay, please stay tuned. 10 minutes.
What? Right timing. It was not time. Exactly. Yeah, not at all. Now